I continue with proof of the theorem. First, again, in this direction, we use Dini lemma. Consider functions. Well, first step is the same. Item A is the same as in theorem 1. Consider closure of M with line, and is compact. Norm is continuous function. On M. So exists maximum of norm function f in M. Let's see then for any f from M, here M over line, and from M f from M, it implies that norm f less or equal to C. And second, so it is A. For B. For B, consider functions f capital N on overlined M. By definition, I construct this function as follows. Supremum while x minus y less than 1 over n, fx minus fy, that's all. So it's easy to see that only I change the parameter, continuous parameter delta in B, in equicontinuity, by discrete parameter 1 over n. So what we can say about this set of functions, family functions? Moreover, it is sequence of functions. Of course, it is tends to the 0 as n tends to the infinity because f is continuous. Yes. And second, we need to check that these functions are continuous too. So let's consider the difference of values of these functions for the different continuous function, f small and g small. It is minus the same expression for function g small. Then, because all differences are in modulus, these differences are symmetric, so I can, without loss of generality, assume that this is larger than this, and in this inside the f of x is larger. So I can use, so here the shim minus g of x plus g of x minus g of y plus g of y. Put here these elements and use the triangle inequality. Use the triangle inequality, so we obtain that the fx minus gx, it not depends on y, but I will write that we'll take supremum for x minus y less. Then plus what we have? Gx minus gy. G of x minus g of y. Again, by the same set, then plus this g of y and take here minus f of y. And again by all these elements. And minus this element, what was minus? And we can see that this is subtracted by this. So, and what we have the following estimation. We have restriction that, well, you see that this difference does depends on y, yes? But we have restrictions for x minus y less than 1 over n. This is the same term by changing x on y. So by symmetric difference, it is the same. And of course, it can be estimated by 2 maximum f of x minus g of x while x lies in AB. It's just 2 norms in CAB. So it means that our function fn are continuous. So by Dini lemma, we conclude that fn tends to the 0 uniformly on M with line on compact set and on our set M. And this is just property B with changing delta on 1 over n. That's all. So this step is, I think, is finished. Second direction. Again, idea, construct for any epsilon positive, finite epsilon network. And then use Hausdorff criterion. Okay. For complete for more easy way, let's assume that function. Let's consider real valued functions without loss of generality. Without loss of generality. Let us consider real valued functions. In another way, consider f of x equals u of x plus imaginary unit multiplied on v and x, and repeat for our prove for U and for V. So by A, there exists constant C, positive, that for any f from M, maximum f of x less or equal to C. And by B, for any epsilon positive, I repeat the definition of equicontinuity for any xy from AB such that but here I take not epsilon but epsilon over 3 in order to finish to obtain just epsilon. Then take any subdivision of AB, take subdivision of AB, so it is T equals Ti, I from 0 to N, T0 equals to A, let's inverse, beta, A equals T0 less than T1 less than T2, etc. less than Tn, just B. And for any I possible, Ti minus Ti minus 1 less than such delta from B. For I equals 1 to N. And construct, just it is more easy explained in picture, but construct such some lattice, yes, on it. So such. This is x-axis. This is y-axis. Let AB be positive, it is doesn't matter. A, B, it is T0, T1, T2. Here C, here minus C. All graphics lies in this rectangle. One line. Second line. So vertical lines is difficult to write as lines, but horizontal, I think, without this. Here, vertical lines. Here, you got horizontal lines. Take such lines that this is epsilon over 3. And maybe the last line, maybe you may longer, for example, C with tilde, such that was the last, for example, you may finished here, but this is for this epsilon over 3. And the same up. So we have a set with finite numbers of intersections. So we have finite number of nodes, yes? The nodes at the intersections of these lines. So then consider set Y, G of X, piecewise linear functions. Passing through a node of our net. For example, this, and this. Yes. Or this. Because we have a finite numbers of nodes, the set Y is finite. Let us take element number point T from Ti, Ty plus 1. And try to estimate Ft minus Gt and G from Y. So by triangle inequality, it is less than Ft minus Fty. So let's one picture show Ti plus 1, and here number T, yes? Plus Fti minus Gti and plus Gti minus Gt. This less than epsilon 3 by equicontinuity. This less than epsilon 3 by choosing function g. And this is less than epsilon over 3 again by property. Property of the set Y.
So finally, we obtain the estimation by epsilon. So the set Y is finite epsilon network. So by Hausdorff criteria, set M is precompact. So that's all. So we finish our theorem, and additionally, I formulate theorem 3, but without proof. Without proof. Set M in LP AB, where P is from this diapason, is precompact if and only if, again, two conditions, both conditions. A, M is bounded, and B, for any epsilon positive, there exists delta positive. For any H such that absolute value of H less than delta implies that for any F from M, it is equicontinuity in average, so-called property. Integral from AB fx plus h minus f of x powered p integral Lebesgue d mu 1 over p less than epsilon. So it is so-called equicontinuity in average. If some remark, if x plus h does not belong to our interval, fx plus h is 0. So we can use this theorem without proof, and I finished the lecture part. So first problem was show that standard sequences where we have the unit on the cuff place is basis in LPS and not basis in here, yeah? This is easy. L infinity is not separable. So there are no, it can't contain the countable basis. Yes, but an LP with finite P, let's take X from LP, X equals X1, X2, Xn, and so on, not 0, and so on, and so on. And consider representation X. Of course, it's a system EK is linear independent, yes. Let's consider set Y capital looks like with rational coefficients, and n is arbitrary natural number. What you can say about the power? Oh, sorry, I just begin to prove that it is separable. Of course, this representation is unique because we have the fixed coordinates, and let's try to find this difference. Of course, it is equal by our representation. The sum from the index n plus 1 to infinity, powered p, and then again powered 1 over. And it is tends to the 0 as n tends to infinity by definition of LP. Because x lies in LP. So we have the partial sums tends to x. That's all. And again, repeat, L infinity is not separable, that's no basis. Is it clear? Second.
Yes, it's clear.
Okay, do we need to discuss the second task?
Well, if you don't mind, sir, yes. Thank you.
We know that M orthogonality is linear closed space, subspace. Yes, we prove it. Okay. So by duality, it is easy to understand that then contains the span of M and it's closed. Yes. So let's try to obtain two different representations for H. For example, we can say that H is equal to M closed plus linear span, closure, and orthogonal. It is just for theorem, but by theorem. Then M here. What another representation we try to obtain? And then from another, it is M orthogonal. We know it is closed space plus this. But M orthogonal coincides with this space. How we can show it? First, of course, M lies in this set, yes? So for the orthogonal complements, we have inverse embeddings, yes? For inverse, we have, for the orthogonal complements, we have inverse. But if X lies in M orthogonal, what it means? It means that y equals to 0 for any y in M. But then X alpha y1 plus beta y2 equals alpha x y1 plus beta x y2 equals to 0 for any y1, y2 from M. Yes? So we obtain immediately that X lies in M square. But we know that orthogonal complement is closed. Is closed. And again, we'll repeat the proof of the continuity of scalar product. So X lies is in here. So we obtain, so M orthogonal coincide with this. So we have that these parts are the same. Yes? So because we proved that the uniqueness of this decomposition on orthogonal sum. So we obtain that what we need. So is it clear? Okay. So third problem. Third problem is let's take black. H is Euclidean. Something with the pencil. H0 is closed subspace, and H is not the sum of H0 and H complementary, orthogonal complementary. Let's take H, for example, C minus 1, 1, but 2 is here. So I take the matrix scalar product FG equals minus 1, 1 real functions. And take H0 equals, we know that the norm will be F minus G here equals Fx minus Gx squared dx 1 over 2 minus 1, 1. We have, do we have a problem that C1 is not complete? I think we discussed it on the first lesson. Yes?
We had discussed it. On first lesson. So the same C2 0 1 is not complete. And just now I can describe the subspace H0. Subspace H0 is such function f from continuous function minus 1 1, real continuous real function with metric. Such that f of x equals to 0 as x belongs to minus 1 0. You can show this open, for example, but function f is continuous. So in C2, in class of continuous function, it is closed subspace. It is closed subspace. And it is, you can take just here. But H0 orthogonal complement, for example, it's easy to check that it is function that is 0 as x belongs to this subinterval, subsegment, half of segment. And we see that H0 plus its orthogonal complement is just function from C2 minus 1, 1, but f at 0 equals to 0. So it not coincide with whole space. Okay?
In this example, is it that x belongs to minus 1 to 1 in the third part? In the third part, is it true that in this x belongs to minus 1 to 1?
That's important. You can take any interval and divide it on two subintervals. So interval minus 1, 1 is not important. Or your question is another. Maybe I don't understand.
Yeah, can you elaborate on that?
So what about the fourth problem? Or not square. Square we can calculate on the previous seminar, yes? And here we have fourth power. So let's take again L2 minus P, basis sine and cosine. And f of x take equals to x square. It is even function. So it is even function. So sine Fourier coefficients equals to 0, yes? Because sine is odd function. So we need only calculate f0. It is 1 minus px square. It is Fourier coefficient for first function, 1 square root 1 over square root of 2 pi. It is equal 1 over square root 2 pi to x cube over 3
from 0 to pi, because we have an even function. So it twice the integral. So it is 2 pi third over 3 to pi. I don't simplify it just now. So Fn equals 1 over pi minus pi x square cosine nx dx. 1 over pi, and we need to calculate by parts 2 times. X square sine nx over n in limits pi minus 2 square pi 1 over n x. So check please by calculation. Sine nx. Sine. A sign in the integer pi is 0, so it is 0. Here I rewrite it is x d cosine nx, then I change here square, and here take plus, because derivative of cosine is minus sine. And again by parts, 2 over pi n square, x cosine nx pi minus pi, minus 2 n square minus pi. Derivatives put on x, then we have cosine nx dx, periodical function whole period, so it is 0. And then we obtain only what? 4, because we have an even function and symmetric. 4 pi minus 1 power n cosine and integer pi, and here square root of pi n square. So let's Parseval equation. Let's f square minus pi x4 dx equals 2x5 0 pi 2 pi 5. So 2 equals f0 square I write it again, just what we have. 4 pi power 6, 9 multiplied to pi. Plus sum. These signs doesn't matter. 16. Something strange, because I have something not homogeneously on power of p. Yes. Is my calculation of Fourier coefficients 1 over n is correct or not? Maybe. Square pi square. Yes. Pi n 4. So we can something simplified. Here we have only two. Here we have 5. And here we have 9 plus 16 pi and our sum. What we need. So we obtain so 10 minus 5, 4, so 45. And finally, what we have here, we have 8 pi over 45 equals 16 pi and our sum. Is it clear? Moreover, you can calculate it is always P to K and some numbers which is connected with Bernoulli numbers. Bernoulli numbers are the same, L2 minus pi pi, the same basis. And F equals X power K. Is it clear? What about the fifth problem, 5? Who can calculate this sum? So let's take again L2 minus pi basis. Here I take basis with complex exponent. Where n is integer. And let's take function f of x equals let's take minus x. Think. Let's try to do it. Let's try to do it. So square root 2 pi fn, it is square root 2 pi, or so scalar product without this, just with exponent. So it is from minus p pi e minus x here minus e and x dx. I emphasize that the second term in scalar product is a complex conjugate. So it is integral equals
This is not correct. Here minus, yes. Let's change it. 1 plus en pi minus e 1 plus en minus pi. Let's use this formula. And like to try to find the modulus, the absolute value. So it is equal to and here we see our in denominator we have just we need in the sum, you see, yes. So if you take absolute values, you see that this term doesn't matter. This term is same, and this is equal square root so it is 2 times take the hyperbolic sign, so called sinus, and then but here I emphasize that we have an integer numeration. So non-zero element 0 take twice, are doubled, and for n equals to 0 we have an additional term. And the norm of the function f square, so I take minus x. I think you can take an exponent in the power x. So it is equals minus 1 over 2. So it is so you can write it as in the following. I take this denominator to the sum, so I obtain 2 cosine. So let's write Parseval identity. F0 square plus two squares. 2 because for negative and positive n we have the same formulas. So it is, let's continue. F0, where we have F0, F0, it is, we take from here to 4 hyperbolic sine square
over 1 over square root of 2 pi. Don't forget to divide on this. So here we have 2 pi plus 2 sums, 1 over pi, and here sum 4 sin square p, sum 1 n square, n equals from 1 to infinity. So divide on the hyperbolic sign and on two hyperbolic sign, I think. Here we have cosine, here we have sine, not only on sine. So we have 2, so here we have 2, because we have plus, no, again, I see correctly was. The first step was correct. Cosine hyperbolic. Here we have sine hyperbolic first step, first power. Here we have 2 over 2, and we divide, and we have twice sine hyperbolic over pi. And our series. And finally, we obtain hyperbolic cotangents of pi minus. That's all. Who wants to understand how to do, try to calculate. Where a is positive. For any positive a, so previous example, a equals to 1. That is previous example. Okay? And what we need to consider again from the sixth so what I take as h0, I take 0 at negative subinterval. So let's try to find h0. Let's try to find the h0 orthogonal. We know that f, all f, are 0 on the negative subinterval. By definition of the scalar product in Sobolev space, in W, 1, 2. This must be 0. This integral I write as df. Sorry, my 0, 1, 0, 1. And try to calculate by parts, to take this integral by parts. So it means the minus so we obtain the following. This must be 0. But this is element, this term is 0. So when it can be 0? For example, we obtain such problem. And so try to find the solution. Not in the exponents, but in hyperbolic function. Define as g equals a hyperbolic sine plus b hyperbolic cosine. I shift the variables because it's better to calculate it's in right end of the interval, in the right end of the interval. But the shifted hyperbolic functions, it's again a linear combination of hyperbolic functions. So we have two-dimensional space of solutions, and here we have a linear combination of two independent solutions. And g derivative equals a plus b. So g derivative at 1 equals to a. It must be 0. So a is 0. So g, function g, is b. But where? We have integral on 0, 1. So it is on 0, 1. And some function, arbitrary function, but in w minus 1. On 0 minus 0, 1, but in Sobolev space. So it is must glue in the center of the in the 0. So here we have some function g minus 0 must coincide b so b equals g of 0 divided on hyperbolic value of hyperbolic cosine in y. So we have description of our orthogonal complement. It's such function g from w1 to such it's g equals g of x equals g of 0 cosine 1 cosine hyperbolic x on y on 0, 1 and arbitrary from on arbitrary from 0 minus 1 0 on minus 1 0. And by constant b they are continuous at 0. But what we want to check, by this calculation, I tried to find orthogonal complement in class of more smooth function. If you see, I obtain the differential equation of the second order. So I find the orthogonal complementary with the assumption that our function have two derivatives. Why this is an orthogonal complement? It is to show that it is all. We need to show that it is all complementary. So we need, if you take f from a Sobolev space, we need to obtain f0 from h0 and f1 from our candidate on the orthogonal complement. So by definition, we see that for any function you can find f1, we take f1 as f0 So we define f1 as following. You see that it is functions from double v 1 2 minus 1y. It is continuous at 0. It is continuous at 0 because hyperbolic values of hyperbolic cosines at 0 reduced. And f0 is just f minus f1. And you see that f0 on this subinterval equals to 0. So it is real from h0. So you divide all space in the sum of two subspaces. So it is really all complement, orthogonal complement. Is it clear? Is it clear?
Yes, I think.
Okay, so let's try. Let's begin the discuss some problems on U topic about two problems. I think we discuss about we can have we have time for two problems. First problem, let's consider M is such function, such sequences from LP, such that xk less or equal for some numbers ak, where ak is fixed
sequence. Show that M is precompact if and only if. What is your conjecture? It's so-called parallelepiped in infinite dimensional space LP. When these edges of this parallelepiped AK, this is half of edges, it belongs to LP. First, it is easy. This is easy. What we can say about the norm? But let's add to the conditions that P is finite number. Then by majorand, we can write it here. Change xk by ak. It's a majorand, so it is positive numbers, not negative. So we can, by definition of set M. So it is, as it is an LP, that is converge. And if we want to write the tail, again, by the existence of majorands, you can change arbitrary x, so it is for any x from M. AK P1 over P, sum from Kn plus 1 to infinity. So it is less than epsilon. You can say that for any epsilon there exists n, because AK, sequence AK is from LP. Second, from opposite. From opposite, let AK is not from LP. But from the definition of M, we can conclude that all these numbers are non-negative. So then, if you write the partial sum, the partial sums for AK, it tends to the plus infinity as n tends to the infinity. Then consider elements xn from M, which looks like A1, A2, AN, and then 0, 0, 0. It is finite sequence, so it is from LP. And moreover, it is from M by definition. But it's xn. But the norm xn tends to plus infinity, so set M is not bounded. So it is contradiction. And the second problem, investigate system Fn x equals to xn
n from 1 to infinity on equicontinuity in space C01 in class of continuous function on interval 0, 1. Of course, it is clear that the norm equals to 1 for any n, the maximum point at 1. So it is bounded set. So for precompactness, we need to check only equicontinuity. What you can say about the equicontinuity? Let's take x equals to 1, y take equals y 1 minus delta over 2. So x minus 1 equals delta over 2 less than delta. And let's calculate fnx minus fny equals 1 minus n. And we know that this number less than 1. So we can say that there exists n such that 1 less than 1 over 2. Then we immediately obtain that there exists n, that fnx minus fny not less than 1/2. And we have a contradiction with equicontinuity. That's all. So homework, but try to do it yourself. First, let's consider ellipsoid in L2, small. Infinite dimensional ellipsoid. Show that it is precompact. If and only if sequence AI belongs to C0 when it tends to the 0. Second problem, let's consider nx is precompact or no in C01. The same question. Fourth,
the second set the same, but the norm, the derivatives are bounded in the sense of L2. And ABC, sorry, Latin numeration, A, B, and C. And third, such function from C1, AB, here 1, such that, like ellipsoid, but in class of continuous function. A, B. C, C1, C2, some non-negative numbers. Fixed for each space. Fixed for each set. What you need to do, investigate on precompactness. M1, M2, M3 on precompactness. 5 problems show that unit ball B01 from L201 is not precompact set in L101. But understand that L201 is embedded in L1. And last, show that unit ball from space C1 is precompact set in C01, and from W1 to 01 and L2 01. It is A, it is B. So I think it's sufficient, because with sub items you have a lot of tasks, but try to solve something. I think that's all on today. Some questions?